Okay, so today I'm going to present on nonlinear regression. So here's just a general outline of the presentation. So first I'm going to go over the background and general overview of nonlinear regression. I'm going to go over three different topics of it, three different types. There's logistic, ordinal, and Cox regression are three very common ones. And then some honorable mentions. I'm not going to go so deep into those. I'll just kind of briefly discuss them. So those three in the middle are ones that I use all the time. So I think that in medical research, ever since I've started here, I probably used logistic regression more than any other regression type. Ordinal regression and Cox regression, I probably use those like at least 1 or 2 times for studies each year. Those are really good too. And so this is going to be broad enough that hopefully you'll get a good idea of what's out there. But it's not going to be so in-depth that you'll be able to just like replicate it and start doing it on your own. So these do require a little bit of self-study. Okay, so background. All right, so nonlinear regression versus other types of parametric analyses. So, there's different non-parametric stats for like dichotomous outcomes or like non-normally distributed continuous variables or ordinal variables. And those are all good methods, and they usually involve a chi-square test at the end. So why do we need nonlinear regression? So it allows for multiple predictors in it at once, and these can be different distributions. You can have, for example, 2 categorical variables, 2 continuous variables, or 1 of each. It allows for interaction effects between those variables to let you ask a different set of questions. So for example, you may be curious as to whether a protocol is more effective or less effective for certain groups of patients. Does the screening protocol help more for obese patients than non-obese patients? And so that's an interaction effect. But in general, really, it's the same thing as whenever you're deciding whether to use a linear regression or like a t-test, for example. Same considerations apply there. So there's reasons to use linear regression. It's got a lot more flexibility, can do a lot more with it than a t-test. So there's something called the general linear model, and that is like an umbrella term for like linear regression, ANOVA, things like that. In parallel, there's something called the generalized linear model. And a lot of the techniques we're discussing are going to fall into that, pretty much everything except for Cox regression. And with that, it's sort of the same. So with a general linear model, there's supposed to be this linear relationship between predictor variables and your outcome variables. Here it's sort of the same thing, but there's a linear relationship between predictor variables and some function of your outcome variables. And so with logistic regression, that function is going to be the natural log of the odds of the probability of an outcome. And so that's why odds ratios are important in logistic regression. Anyway, so I just wanted to bring that up, just kind of help you understand that term and see if, it comes up a lot. So throughout this presentation, I'm going to use one database, so this is a study for one of my student projects for this year from oncology group. And this is just to provide continuity. I'm going to use the same example database throughout, even though maybe all the analyses aren't going to be the best way to do it using that, but just to kind of give you some continuity so I don't have to keep explaining the different studies. So what this is that in oncology, a nutritionist and one of the physicians developed this glucose protocol for hyperglycemia screening in patients who had leukemia and lymphoma. And so the idea, well, I'll get to the idea a little bit later, but first, just the data. There's 154 patients, and then 57% had glucose, 35% developed hyperglycemia at some point, and you can see this cross tabulation there. Just eyeballing, you can see the protocol groups maybe a little bit more likely to have hyperglycemia. You have to test that statistically, of course. The question is, Was the glucose protocol effective in early detection of hyperglycemia? So this is the research question. Here's some challenges here. So, if it's more effective in detecting hyperglycemia, we might expect that those under the protocol group are more likely to have hyperglycemia diagnosed, which is what we're sort of seeing there with that trend there, 41 versus 27%. But, that's a little bit limited in the fact that not everybody's going to have hyperglycemia. So that's a limitation there. And there's also the important factor of time. The protocol is especially good at detecting early on. And so the earlier, the better for this diagnosis. That's not really accounted for in just this dichotomous, yes or no variable here. And the other thing is that time is working against us because the no protocol group is a historical control. So they have more follow-up time than do those in the protocol group, and hence are more likely to develop hyperglycemia somewhere along the way because they have more years of follow-up than do the protocol group who are more recent. The protocol was instituted in 2019, and so our historical control group going all the way back to March 2018 had more follow-up time in general. So that's something that's kind of going against us if we're doing this dichotomous diagnosis or not. Anyway, so those are some of the important points to understand about the data before we proceed. So first, we're going to talk about logistic regression for a moment. In general, for the outcome and effect size, an outcome variable, ordinary logistic, just plain straightforward, the most simple logistic regression models are going to include a dichotomous or binary outcome variable. This could be diagnosis of hyperglycemia, for example, whether a patient had a symptom. It could be anything, whether the patient survived or not, relapse, anything like that. Some people in the past, I think there was a trend for a long time, and it's kind of not being used so much anymore, is this idea of a median split. So you take some continuous, maybe non-normally distributed variable, and you split it by the median. So the 50th percentile, those below are in one group, those above are in another group. Well, you can do that, sure. You lose a lot of information because, encoded in that continuous outcome variable, there's a lot of information that's going to be just kind of taken away whenever you're just splitting it into two groups. And so it's not very powerful, not a good way to do it. You lose a lot of information, and it lowers your power to determine whether there's a significant effect. And it may also be a little bit less intuitive to interpret. The meaning may not be so great, like the meaning's not necessarily always clear. Generally a bad idea, the median split. Okay, the effect size is an odds ratio. And I mentioned this thing about the log odds is the link function for this logistic regression. And so odds ratios are really important for that. And this is the effect size, meaning that so with odds ratios, if you have an odds ratio of 1, that means that there's really no difference between two groups. An odds ratio can be anywhere between, it can't be 0, but it can be above 0 all the way to infinity. And there's this sort of reciprocal relationship so that, like, for example, an odds ratio of 5 is the same effect size as an odds ratio of 0.2, because 1 divided by 5 is 0.2. And so those have an equal effect size in terms of the strength of the relationship. It just is that, instead of your outcome being survival, it's death, for example. You just flip the outcome, which one you're looking at, but it's the same effect size. All right, so an odds ratio, it gives you an idea of the effect size. An odds ratio of 2 is a pretty decent effect. The bigger the odds ratio, the more profound the effect. All right, so here's just an example. This is a frequency table, a cross tabulation of This group is the kind of X variable, the independent variable. The outcomes are like the Y variables, the dependent variables. And these are frequencies. So there are a number of patients in group 1 who developed outcome 1, and so each of those 4 different groups are numbers. They're not percentages, they're not probabilities, they're just number of patients. And so an odds ratio, so it's the ratio of 2 odds is what it is. And so an odds is the probability of something occurring divided by the probability of that thing not occurring. And so, I'm not clear on the formatting here. I don't know that I've seen this formatting, the parentheses with the pipe in the middle there with regards to odds, but it's something that's used in a lot of things like expected values and for our purposes here, probabilities. And so what I'm trying to say here for this first one is odds ratio equals the odds of outcome 1 given that you're in group 1 is the numerator here. Okay, so that's the first odds. And so odds of outcome 1 given group 1 would mean that you take the conditional probability of being an outcome 1 for group 1, and that's going to be A divided by A plus B. Okay, so all in group 1, A divided by A plus B, divided by the probability of that not occurring. So still in group 1, but the probability of it being outcome 2, which is B divided by A plus B. And so that there in the numerator, those two sets of fractions in that numerator are going to be the odds of being an outcome 1 given that you're group 1. Okay, you divide that by the odds of being outcome 1 given that you're group 2. And you can see that similar logic applies there. You have that denominator. Okay, those denominators, A plus B, C plus D, they cancel out to where you're left with A divided by B divided by C divided by D. Okay, and then, flip it around, you get A times D divided by B times C. And I bring that up and kind of show all that just to say this is a formula I use a lot. Just a quick hand, I actually use it a lot developing this presentation. A times D divided by B times C. Convenient for just really quickly in Excel computing odds ratios. So we're going to apply that to the hyperglycemia study. So, the odds of being in hyperglycemia given that you're in the protocol group divided by the odds of being hyperglycemic given that you're in the no protocol group. And so, you can see plugging in those numbers from that table, the frequencies, not the percentages, is 36 divided by 36 plus 52, and so on. Like I said, that first one, the 36 over 36 plus 2, is the conditional probability that you're hyperglycemic given that you're in the protocol group. So that's 41% really is a way to rewrite that whole little fraction there up on the top. Anyway, so you reduce it, you use the little, cancellations things, and you get an odds ratio of 1.85. So the odds ratio is 1.85 for that analysis. All right, so let's write it up. So here I've given like a little chart, a stacked column chart of hyperglycemic and non-hyperglycemic patients, stratified by whether or not they were on the protocol. And you can see these are the frequencies on the y-axis there, and I've put in the label there for the percentages of patients in the hyperglycemic category for each of those groups. The interpretation here with this logistic regression that I performed is that those with versus without the glucose protocol were not statistically significantly more likely to have been diagnosed with hyperglycemia. And then I put in the percentages for each groups of being diagnosed with hyperglycemia, and the odds ratio, 1.85, which I just computed. P-value is not significant. P equals 0.081, so not less than 0.05, not significant. Again, this totally discards the time factor, the fact that, as I mentioned, time's kind of working against us here. And again, we are not hypothesizing that they're more likely to actually develop hyperglycemia, but we're hypothesizing that we're more likely to catch them developing hyperglycemia, more likely to correctly diagnose them, not miss a diagnosis. So This has a number of shortcomings that I just mentioned, so not the best way to test this, but it is an obvious choice, maybe a first obvious choice that you thought of, and it was actually the first one that I thought of whenever I was actually running these analysis for the study. We got to control for time somehow. All right, the next one that we're going to discuss is called ordinal regression. And this is a very good technique, and this is probably the one I'm going to go over that's maybe the least commonly used, probably the least commonly known. I'm going to guess that most of the people here have heard of logistic regression, and I'm going to guess most of the people here have never used ordinal regression. And maybe you haven't heard of it. So an ordinal variable is one that is, there's a finite number of outcomes that a y variable, a dependent variable, can have, and they're ordered in a meaningful way. So for example, if you take a questionnaire and they have a Likert scale from strongly disagree to strongly agree, that's supposed to represent some sort of underlying latent variable of how you feel about something. And you have 5 categories. And so theoretically, the meaning is that the higher the rating on that scale, the more strongly you agree with it at each point. You can compare strongly disagree to disagree. If you disagree versus strongly disagree, you disagree a little bit less. You agree a little bit more with that item. Stages of a disease, like 1 to 4. And here we have pancreatitis in our study as one of the variables that I'm not going to mention, not going to go into here, but that was, I think, 5 categories of pancreatitis. So that would be another good example of when it would be appropriate to use an ordinal regression. For this first example, Likert scale item, if you're just looking at a single item on a scale, you could use ordinal regression. That would be the best way to do it. If you use another technique, that's probably not the most appropriate technique. But, with psychometric scales, usually you have several items and you sum them up, and then people just want to do a linear regression on that. And maybe that's the best way to do that. But with a single item being your outcome variable, the ordinal regression is the best way to go, probably. And I mentioned that the median split in a logistic regression is not a very good method because you lose so much information. Well, if you were instead to take quartiles, four groups with equal frequencies, or relatively equal frequencies of patients within each of those groups, each of them have about 25% of the population, or the sample rather, or quintiles, each has 5 different groups, 20% of the population in each group, the sample. This is actually not a bad idea. If you have a super non-normally distributed variable and, it's not working out to where a transformation or something's appropriate to do a linear regression, this is actually a very powerful method. You gain back a lot of the information encoded in that continuous variable when you group it into those categories. It's not necessarily as good as like a just straight up linear regression with a perfectly normal distribution, but if you've got some kind of very skewed distribution, this really isn't such a bad idea. Interpretation may not necessarily be the best, but especially if those quartiles are meaningful, you're talking about quartiles of like income, salaries, and things like that. People do use quartiles for those sorts of things, and in a lot of cases, it's something that's one of the good techniques you can use, and it's pretty powerful, like I mentioned. Anyway, so with with ordinal regression, there's a lot of different models you can use, a lot of assumptions, and just based on what I've read, this proportional odds model assumptions, one that's used pretty frequently, maybe the most, and it's just the one that I ended up kind of sticking with and using, but there are some alternatives. I just think this is the one that's most frequently used. So in this model, there's a proportional odds assumption, and this is a little bit of something that's kind of hard to understand at first. And so this single sentence that I have there at the bottom is the best sentence I could find. It's like a single sentence to describe what we're trying to explain. The unit the effect of a unit increase in the independent variable, for example, from strongly disagree to disagree, results in the same increase in so a change in the predictor variable, for example, from being in the no protocol group versus the protocol group, will result in the same increase in odds of a dependent variable, this Likert scale, for example, increasing one ordinal value regardless of the ordinal value. So it could be from strongly disagree to disagree, or from agree to strongly disagree. So that change in the odds ratio between the differences in those odds ratios between two different categories is going to be the same regardless of your starting point. So some example analyses here. Instead of doing it like you've got diagnosis, no diagnosis, we're going to try to account for time by saying diagnosed during induction therapy, which is the first phase of therapy for these patients that we're studying here with, these cancer patients with these defined conditions that we're studying here. So you have diagnosed during induction therapy. That's our first category. That's the best case scenario in a way of looking at it, because you're diagnosed early. The second best case scenario is that you're diagnosed during induction therapy, after induction therapy. The third case scenario is you're not diagnosed at all. And so to call this an ordinal variable is sketchy at best. This isn't necessarily the best example of an ordinal variable. I wanted to include it just because it's continuity, using the same data set, and we'll find in a moment that it actually does a pretty good job of modeling it. But, to say that no diagnosis is, just is ordinarily, is this third category, that there's an ordinal relationship between these three different groups, these three different categories, is a pretty big stretch, because if you're not diagnosed, it may mean that you don't have hyperglycemia. It doesn't necessarily mean that you missed it. But setting that aside, we're going to pretend that this is a good way to use ordinal logistic regression, and we're going to examine the results. So some example analyses here for this one is, so first in this top box there, I've got two different odds ratios. Okay, so the first one is the odds ratios of being diagnosed during induction for the protocol versus no protocol groups. That's our first odds ratio. And if you look at that table there at the bottom, what we're doing is we're comparing the diagnosed in induction is one set of frequencies, and the bottom set, the other group, is the either being diagnosed in after induction or not having a diagnosis. So it's the first row versus the second and third row. The second odds ratio up there, induction or after, is going to be, the first two columns, the first two rows versus the last row, again, stratified by protocol. So we're just going to look at that. And by the way, the assumption is that these two odds ratios are equal. That's the assumption of the proportional odds model. Breaking down that first odds ratio, you have on the right side of that equal equation, right side of the equal sign, you have diagnosed, the conditional probability being diagnosed in induction, given that you're in protocol, divided by the conditional probability being diagnosed after induction, or not having a diagnosis at all, given that you're in the protocol group. And then the same logic applies for the bottom part of that in the denominator there, except for the condition is that you're in the no protocol group. So if you look at those percentages down there, you have, you can see where these percentages come to. You go through just the denominator of those percentages there. You've got 24% is the induction protocol group, and then 17% is the after induction protocol group, plus 59% no diagnosis protocol group. And do you do the same thing with that no protocol column? Anyway, all that to say, you get at the end up with 2.64 as your odds ratio for that first set of odds, that first odds ratio that we're looking at. Okay, and so then for that rightmost one, you're comparing being in either the diagnosed during induction or after induction, and you're comparing that to the no diagnosis group. So the first two rows versus the third row. And that odds ratio was 1.85. I didn't do the math here on the slide, but it comes to 1.85. And the assumption is that 2.64 and 1.85 are the same, and the proportional odds assumption. So just to kind of point this out, 1.85 is the same as the logistic regression odds ratio that I had presented a moment ago. And the reason for that is that, like I said, diagnosed in induction or after induction versus no diagnosis. So essentially we're comparing, are you diagnosed or are you not diagnosed? And that's what we did with the logistic regression. And so that's why it's the same number that comes up. So this assumption, like I said, 2.64 is supposed to be equal to 1.85. Nothing's ever going to be exactly equal whenever you're doing this with real numbers, real SETI data. They're always going to be subtly different. But are they different so much that this proportional odds assumption is not tenable? Well, in this case, there's a score test for the proportional odds assumption that at least comes through in SAS and R, but it probably comes through in SPSS too. I've never used this method in SPSS, but it comes out to chi-square degree of freedom 1 equals 0.89, p-value of 0.35. And if it's not statistically significant, then the proportional odds assumption is not being violated per that test. So basically that is a green light to say that, yeah, the proportional odds assumption is probably okay in our case, even though the numbers are a little bit different. They're close enough that it is not statistically significantly a problem. And so good to go with that. And here I've broken up that same, you may remember that stacked bar chart with just diagnosis versus no diagnosis, the black being the diagnosis, the no diagnosis is the white. Here I split up the diagnosis being the white. I split up that white category, 41%, into that 17 and 24% for the protocol. 17% for the diagnosed after induction therapy, 24 for the induction therapy diagnosis. I did the same with the no protocol group. And here you can, yes.
On the odds ratio one, you made the point of you're using a count rather than a percentage, and on the proportional odds, you're using percentages. Did I miss why you can do that, or why do you do that?
Yeah, that's a good point. Honestly, I did that for ease, for not having to show a bunch of numbers. But the idea here, and it is a very good question because that's probably confusing some people here, is that, like, for example, this 36 divided by 50, 36 divided by 36 plus 52 is equal to 41%.
Is 41%. Okay, sorry, Tyler. Yeah.
Yeah. So that's a good question, but essentially I did it for ease.
Okay.
I did think about it, and I was like, yeah, that might confuse some people, but I'm going to go ahead and do that anyway.
You did. Sorry, I got it now though.
All right, thank you, and thanks for helping to clarify that. Alrighty, so yeah, it's a good question. There we go with this. So the idea here, and this is what we want to see whenever we're doing a proportional or whenever we're doing ordinal regression. So if you look at it, the green, 24% versus 11%, more likely to be in the green category for the protocol group versus the no protocol group. You can see in the middle there that diagnosed after induction therapy, 17% for both of them. So they're the same. And then it flips with the no diagnosis group. The protocol is less likely to be in the no diagnosis group, 59% versus 73%. That's what you want to see with this ordinal relationship. Okay, that one group's on one pole, the group is more likely, the protocol group's more likely on the one pole, one extreme pole, the green, the diagnosed during induction. They're more likely there, but they're less likely in the no diagnosis group. So there's this flip, and that's the sort of relationship you want to see between these two variables if the ordinal relationship is to hold. There's a flip, and that middle ground, somewhere in the middle, it kind of changes directions to where one group is no longer the higher probability group for specific categories. Does that make sense? So the results of the ordinal logistic regression that I've done here is that those with versus without a glucose protocol were statistically significantly more likely to have been promptly diagnosed with hyperglycemia. Again, and the odds ratio is 1.97. So again, I say 1.97 is the odds ratio. The proportional odds assumption says there's only one odds ratio. It doesn't matter which odds ratios you're looking at. They're all supposed to be equal. You see the 2.64 and 1.97 that, or 2.64, 1.85 here. Those are the actual literal odds ratios for those groups, but the proportional odds assumption is that really they're the same. It's just, random chance that they're a little bit different in different directions, but the odds ratio overall should be ideally the same between all categories. And so 1.97 is this kind of compromise in between those groups, those two odds ratios. And p-value, I would just ordinarily say p less than 0.05. I just wanted to demonstrate how very borderline this was, 0.498. So this one is statistically significant, whereas the logistic regression wasn't. It's powerful. It's more powerful than ordinary logistic regression when it's applicable. But again, the meaning of this is a little bit suspect, because is this really an ordinal relationship? Is your outcome variable really ordinal? I would say probably not. So the interpretation is a little bit unclear. What does this really mean? We're not really accounting for time in the best way. So the interpretation is a little bit hard to make. And that brings us to Cox regression, which I think is the best method for this approach, or for this question, this problem we have here. So in Cox regression, and if you're familiar with survival curve, that's what we're talking about here. So the outcome variable has a dichotomous or binary event. So in our case, hyperglycemia diagnosis, it could be death. Death is the one that's kind of the quintessential example, the most commonly, I don't know if it's most commonly used, but that's what it's kind of associated with. And that's why you call it survival analysis. So these are events. You have this binary event. You either have it or you don't. And usually that event is a bad thing. Death, relapse, diagnosis. Usually it's something to avoid that you are trying to avoid. Time without it is better. The longer you don't have it, or not having it at all, is ideal. There's the second factor that comes into this dependent variable, and that is time. So you have time to event, time to either event, which is, that negative event we discussed, or being censored out. And so what it means to be censored out is that at last follow-up, as far as we know, the patient doesn't have that negative event. And so with that, you need to record a starting point. This could be the date of diagnosis, the date of surgery, the date of birth, whatever it is you're starting from. In our case, it's the date of diagnosis of cancer. And then you have the date that you have the event, the date of death, the date of relapse, the date of diagnosis of hyperglycemia. Or for those patients who are censored out, you have the most recent follow-up visit in which you know for sure that the patient did not develop that event, that event has not yet occurred. But it's the most recent follow-up that you have for that patient. So you need 3 dates here. For all patients, you need a starting point date, and you need the date of the event. And for those patients who never had that event, you need the most recent follow-up in which you can assure that that patient didn't have the event. And so for our study, we use the most recent visit with oncology, because they are the ones who are really seeing these patients a lot and really testing for hyperglycemia. If you're talking about survival, you can really just say the most recent visit with any clinic visit, or even a phone call with the patient, because that's that the patient's obviously still alive if you have continued contact with that patient. So how long do you have follow-up with that patient? That's the endpoint. So you either have the time from the starting point to event, or you have the time to most recent follow-up for those patients who didn't develop it and are hence censored. All right. And so we had talked about odds ratios, which apply to both logistic and ordinal regression. Here we have hazard ratios. The interpretation is somewhat similar. It's not the same. Hazard ratios is more akin to a relative risk. Odds ratio is the ratio of 2 odds. Relative risk is the ratio of 2 probabilities. For example, it could be the probability that a patient developed hyperglycemia while in the protocol group, the conditional probability there, divided by the probability that the no protocol group developed hyperglycemia. So that's the relative risk. And with hazard ratios, or with this assumption, it is ratio between groups of likelihood of event occurring per unit time, controlling for time, instantaneous relative risk. Think calculus, limit as time approaches 0, it is the instantaneous relative risk, so that no matter where you're looking at within that curve, the ratio of your likelihood of henceforth developing hyperglycemia is the same across groups. The ratio is the same, not the likelihood, just the ratio of those two likelihoods are the same. And so I'll get into what that really looks like in a moment. The proportional hazards ratio assumption is that the relative hazards remain constant over time with between different predictor variables. So yet again, another kind of difficult thing to just kind of understand, just read that sentence and say, okay, I get it. It's something that takes time to wrap your mind around. So I'm going to get into the data then. So this is a very important curve that's used a lot, especially like in survival analysis for patients with cancer, you know. It's called the Kaplan-Meier survival curve. And so this is what they do. This is what they use when they say like a 5-year survival rate. They usually are basing it off of this Kaplan-Meier survival curve. And again, the x-axis here is time and days since diagnosis of cancer. So the starting point is 0. And so the y-axis is the proportion without hyperglycemia. You know, in a survival curve of cancer, it could be like of survival after cancer could be proportion alive at each point. And at starting point, at x equals 0, you have 100% of the patients in either group are still alive. And 100% of the patients in either group do not yet have hyperglycemia because we would have excluded them from our study. That's an exclusion criteria. We're trying to determine how you develop hyperglycemia. So if you have pre-existing hyperglycemia, then we exclude you. So all of our patients are free of hyperglycemia at starting point. And so as you go down, as your x-axis increases along those lines, those curves, then each time the curve dips a little bit, that means one or more patients at that specific time developed hyperglycemia. And so that proportion without hyperglycemia decreases a little bit. And so going all the way to the end, it ends up that like something like 25% of the patients got hyperglycemia and I've stratified it by protocol. In the no protocol group, 25% about at the end had hyperglycemia compared to like 40% maybe in the 45%, something like that in the protocol group. Just going all the way to like that 500 days point. No patients developed hyperglycemia beyond 500 days, and that's why I cut it off there. But so that's what those dips mean. All right, and then the other thing to point out is the sensors. You see these little plus signs scattered throughout. That means that a patient didn't get hyperglycemia yet, but that's as far as the information we have. For example, if you go vertically from like 400 or from like 500 days, you can see a bunch of plus signs, particularly in the glucose protocol groups, that dotted line there. You see all those plus signs there? There's 3 of them. That means that 3 patients right around 500 days already had their most recent visit. So we have as much follow-up as we have at this point with those 3 patients, and as of yet have not developed hyperglycemia. And so they were censored out. That's where the censure comes in. So, and if we were to continue this line onward, I mentioned this thing about this problem of historical controls who have longer follow-up. That solid line, the no protocol group would go on farther because they have more follow-up than do the no protocol group, or than the protocol group, rather. They have longer follow-up past diagnosis than the protocol group because they started earlier, back in early 2018. And so anyway, what's nice here is that this method controls for time. I say the proportional odds that for any unit increase is the same ratio between the two groups. Now, is that proportional hazards assumption acceptable? They would, in a sense, be parallel lines if they were completely, if that proportional hazards assumption were accurate completely, they would be completely parallel in a sense. Now, they can't literally be parallel because you've got two lines starting at the same point and ending at different points. So they can't be completely parallel, obviously. But what that means is that when one group dips, the other group should ideally dip as well, those same exact points, but to a differing extent. A higher proportion might dip in the protocol group than in the no protocol group. It's just that they're supposed to parallel. It shouldn't be that like one group dipped real greatly early on, the other group doesn't, and then just different patterns. And they certainly shouldn't cross lines at any point. That would be a violation there of the assumption of proportional hazards. The assessment, I guess, is that you can see the distances between the two lines. It's certainly not exactly there, but it's reasonable fit, I think, for that hazards assumption. And you can test it with various ways, looking at graphs and things. And it's not a great fit, but it's pretty good. All right. So this time variable that's now being accounted for in the survival curve. Well, just as an aside, one quick way to examine that would be, do a non-parametric statistic that compares just the protocol and no protocol group, the time to diagnosis from cancer to hyperglycemia for those who got hyperglycemia. And here I have the median and range for the number of days. And you can see, looking at that, 7 days for the protocol group versus 113 days is the medians for those two groups. And though that's a really big difference, and it definitely indicates something, it is not statistically significant, because here we're just looking at 54 patients who developed hyperglycemia. We're forgetting about those patients who never developed hyperglycemia, and they're not being accounted for in our analyses. That lowers our power because we have a far smaller sample size. We're just looking and excluding those patients. And so that's not the best way to do it. The best way to do it, probably, of all the methods that I'm going to discuss, is going to be this method right here, this Cox regression. So those with versus without the glucose protocol were statistically significantly more likely to have developed or to have been diagnosed with hyperglycemia, 41% versus 21%. This hazard ratio is 1.76, close to the odds ratio we had of 1.85 earlier. And again, so borderline that p-value 0.4996. I had to request extra decimal points from SAS because it was so borderline. And yeah, it was just barely significant. And so yes, we have our significant finding here, and we have probably the best method to use it. And so this is the one I would advocate for, more appropriate than the others. All right, so a couple of honorable mentions. So, and I'm not going to go as far as detail on these guys, but I'm just going to quickly mention a few things. There's something called the multinomial logistic regression. This is another extension of logistic regression. And this is when the outcome variable is not binomial. There's not a yes or no situation. There's multiple groups and they're unordered. So, different races, white, black, Native American, etc., Asian, different diagnoses. Okay. When you have a lot of different diagnoses, cancer diagnoses, and everybody's got one of them at least, then you can do an analysis, what differentiates those diagnoses. That would be a usage of multinomial regression. This is not a technique I've ever used, except for the example I'm about to provide shortly, but it's not something that comes up as frequently. It's not a question that's as usually asked as some of these others that I've shown previously. Compared to the proportional odds ordinal regression method, it's very similar to that, but there's no assumption of proportionality in the odds. And remember, you have that kind of moving odds between the different categories of the ordinal variable, where you're saying, the first one versus everybody else, the first and second versus everybody else, the first three versus everybody else. You have this sort of moving odds ratio. And here you don't have that. You have a reference category. And so every odds ratio is compared to some reference category. There's a little bit of parallel here with ANOVA. If you've got 3 groups in ANOVA, you can have this omnibus test, F-test, that tells you whether there's a significant relationship between this, categorical variable with 3 or more categories in your continuous outcome variable. And so you compare the different categories against some reference category. And it's sort of the same idea here, except for your outcome is the one with multiple categories, and you're doing this odds ratio. You have all these odds ratios that compare to some reference category. So again, going back to this idea of splitting up between diagnosis for induction, diagnosis after induction, and no diagnosis of hyperglycemia. So this is a more plausible usage of this kind of breakdown of these categories as compared to the ordinal variable, because like I said, it's arguably not an ordinal variable. Well, it's certainly a categorical variable with 3 or more categories that are probably not ordinally related, and so the odds ratios here, the obvious choice here for your reference group is the no diagnosis group. We want to compare the diagnosis during induction versus the no diagnosis, diagnosis after induction versus the no diagnosis. And so here would be kind of my brief write-up of it. And by the way, I mentioned, the ANOVAs with the omnibus F-test. You also have an omnibus chi-square test that says, in general, is the protocol predictive of which of those hyperglycemia categories you fall under? And that one was not statistically significant. So really right there, that would be a stopping point for me. I'm going to pretend for now, just to kind of illustrate what this looks like, that was significant, so that you can kind of get an idea of what, write-up might look like in an interpretation if it were. But the stats and the odds ratios and the p-values here are all correct. So anyway, those with versus without the glucose protocol were statistically significantly more likely to have been diagnosed with hyperglycemia during induction. 24%, looking at that table in the protocol, 24% during the induction versus 11% in the no protocol group in induction. Odds ratio of 2.77, p equals 0.034, significant. But not after induction, 17% versus 17%. Odds ratio 1.26, p-value 0.605, not significant. And as a quick aside, I talked about that cool AC divided by AD divided by BC formula, which I use a lot. I actually use that in Excel during this presentation to compute this, just to kind of, I did this in SAS, but I double checked the odds ratios. What that is comparing for that first one, the during induction groups, during induction compared to no diagnosis, you just completely remove the after induction row from this analysis. And then so here you would have, that AD divided by BC, you would have 21 times 48 divided by 7 times 52, and that equals 2.77. And again, for the 1.26, it's 15 times 48 divided by 11 times 52, you get 1.26. Anyway, so that's multinomial logistic regression. Doesn't really come up in practice too much. I haven't had an instance where this is really the best method to use it, just because of the questions asked. And in my experience has been that's not something that's usually asked, the multinomial outcome variable. Another method that you can use in nonlinear regression was for count data. So the outcome variable is a count variable, which means that it's an integer greater than 0. And so the idea here is that you're looking at the number of some event occurring during some fixed period of time. So the number of clinic visits within a 1-year follow-up period, or the number of lab measures, in our case, the number of lab measures that occurred during the first 7 days of induction therapy. And that actually is an analysis that I used in my manuscript that I'm writing for this study here. I decided not to use the models that I'm about to. So the models for count data include Poisson regression model, negative binomial regression model, So negative binomial and Poisson are distributions, statistical distributions like the normal curve or the binomial distribution. Those are different ones and being applied to different to this regression to regression models. Alternatively, you can just do linear regression. Probably need to transform that outcome variable because it's probably a very skewed distribution of number of lab measures. For example, some patients may not have had many, some patients may have had like a ton. And so it's probably not very skewed, probably kind of, probably negatively skewed so that most of them are occurring close around zero, but some of them have an extreme value to the right there, long tail. Anyway, so you want to transform it usually. And so I actually, in my case with the number of lab measures that I was examining, what I used was linear regression because the results were essentially the same. Linear regression is a much more commonly used and understood, probably create a little bit less confusion in the audience if I use that when possible. And the other consideration that I have when using that as opposed to the others is that that was a very secondary analysis. It was not nearly so important as the hyperglycemia business. And so that was just a quick analysis that I was trying to do, but it wasn't something that's the primary focus of my study. So I didn't find the need to do this more, kind of authoritative measure for examining count data. All right, and that's the presentation. So at this point, does anybody have any questions?
I have a somewhat tangential question, Tyler, to something you mentioned early on. The odds ratio of 5 versus 0.2. They are saying the same. They are saying the same thing from different directions, but they look different, right? Is there a standard? Is there a best practice to be able to show that 0.2 and 5 really are the same distance from a point, even though they don't look like they are? I mean, I'm just talking about trying to convey the message of that of what the data are. Is there some different tool you use?
So there's I'm not aware of any like standard rule of thumb or practice that people use, but it's just my experience over the years that a lot of the clinical staff that I work with are, they're not going to necessarily understand that inverse relationship, that reciprocal relationship. And so I try to order my variables in such a way that all of them are greater than 1 for the odds ratios. So example, if I have a lot of univariate analyses I'm doing in a logistic regression kind of lined up and you have all these odds ratios for each of them predicting some outcome variable, and you have a bunch of categorical predictors, you could ask, for example, the outcome variable here is development of hyperglycemia, the detection of hyperglycemia. And suppose you're looking at whether you're on the protocol or not. And you're looking at age greater than 10 or less than 10. And so you can either compare, being on the protocol versus not being on the protocol, or being not on the protocol versus being on the protocol.
Yeah.
That's the kind of flip that makes it, 1 divided by the other number. And so I try to order it in such a way that all of the odds ratios are greater than 1. Again, with the age, you could say less than 10 versus greater than 10, or you could say greater than 10 versus less than 10. So I always try to make it to where they're always greater than 1, those odds ratios.
How big a known problem is this in your world? Meaning, when I do read articles that have odds ratios less than 1, should I assume that they understand what they're doing and they're intentionally doing it that way, or is this they don't understand that people like me don't understand?
I think more the latter, probably. Okay. And in some cases, so for example, like if you're predicting that the meaningful way to present it is that, you're saying that those in the hyperglycemia group are more likely to develop, those in the protocol group more likely to develop hyperglycemia. But if there's some category that the most, in that group, it's very intuitive to have the protocol group is the one that you're looking at and comparing to the no protocol group, because you think they're more likely to have it. Sometimes you think that a group is especially unlikely to have it compared to the other groups. And that may be, especially when you've got like three categories and one's especially likely to not have it, then it might make most sense to have some of those numbers be less than 0 if that's what you're trying to prove there. But given that there is that confusion about the meaning of that reciprocal relationship centered on 1, in my opinion, when possible, it's best to do the greater than 1 for all your odds ratios.
Okay.
Did I answer your question?
Yeah, that was great. Thank you, Tyler.
Thank you. All right. Any other questions?